So hello, hello everyone. Today we are going to see how to perform operations on the device drivers on the device through your own device driver that you have registered. We have to map the user-defined system calls, the standard system calls, to the device driver routines. Basically, this is how it works. What will happen? Basically, this is how it works. What happens is when your application gives some call, then that call basically what happens in device drivers is that the applications will make standard system calls, and for those standard system calls some device driver routines, no, for the standard system call some kernel routines, that is called system call routines, actually execute. What we have to do is we have to make arrangements and interfaces such that when the application will make a system call, that system call should map to your device driver routines instead of system call routines. What I mean to say, that when the applications will make certain calls like open and close, it should not go to the open and close routines provided by the system. Instead, it should execute open and close calls that are call routines that are created by and written by, designed by you, developed by you. Okay, so that is what we have to do. Suppose this is your some system, and in this system you have an operating system, you do ins mode, and you insert some device driver. Okay, there are possibly more than one device driver for different kind of devices. Suppose you have 2 or 3 device drivers for 3 different kind of devices, and all the 3 devices open in a different way. Suppose one of the devices is a CD-ROM tray, one is some other port, COM port maybe, and one is some other device which is connected through some serial port. Now all the 3 devices open in 3 different ways. So you have to specify 3 different ways in 3 different device drivers to open the 3 different devices. Now when the application will give open call, application have to specify what is the device name, and according to the device name, corresponding device driver will be invoked, and the open routine will go into corresponding and the control will go into corresponding open routine, and the corresponding open routine will execute for the same system call, opening the corresponding devices. So depending on the name of the file, the system will be able to identify that you want to go into which device, and the control will go to appropriate device driver, and inside the appropriate device driver, appropriate corresponding open routine will run to open the connected device. If you feel that you have doubt somewhere, you can ask me immediately. Till now you have done initialization and registration, and this was the algorithm that you followed in initialization function, where you have done register device using alloc char dev region. Prior to that, you did allocation using register char dev. Then after that, you allocated some memory for your skull device using kmalloc. That allocated memory must be set to memset, because right now that allocated memory contains null. So I remember that this part we have not done. So let's go to our device driver, open the initialization function, and after you do kmalloc, here we have done kmalloc, we have allocated device memory for NOD number of devices. 2 for checkout for build, 0 for exit script. No. 1 for check-in, 2 checkout for build, 1 check-in, 6 checkout for development, exit, insert mode. Now it's going in insert mode. After you do kmalloc, then you must memset the allocated memory, pointer to by dev, and fill that memory with nulls for this many bytes. Size of dev into NOD. The whole memory is now flushed and there is no garbage in this. After that, we have to initialize device using cdev init and add it to the device table using cdev add. That part we have done. Okay. Now we move to understand few more interfaces, and we will be implementing the open routine. I will explain this to you in a moment. This is what will happen. See this carefully. We have to open the device, which is some kind of hardware. This will be accessible across the kernel through the kernel. We will insert the device. There are some kernel buffers called dirty buffers, which are IO buffers, which are used to interact with the outside world, which is outside kernel. Very first thing we have to do is we will insert our device driver into the kernel, and the inserted device driver will be here. After this, there will be some application running in the user space. This application running in the user space will give the open system call. See this carefully. The application running in this user space will give the open system call, and when it will give open system call, the open takes the file name as first argument. It will give the file name, that is some file in the file system VFS, which will connect to the device driver using major minor number. Okay. The file will connect to the device using major minor number, the driver and the device. So using which when the open call will be given and the file name will be given for this file, it will be understood that why you want to open some device file. Normally when you give the open system call, the control goes to the driver routine. Now, normally when you give this open system call, the control goes to the system call routine. And routine executes and opens some file that is kept in the secondary storage. But your device is not kept in the secondary storage, so the ordinary system call routine provided will not work for you. Instead, you have written a separate device driver routine as part of your device driver. When the open call will be given and the minor number of the file will take you the control to your device driver, then inside your device driver, when the open system call will be given, then inside the device driver there is a driver routine that you have written, and the control will go to this driver routine, and this your device driver routine will execute. And here you will do the opening, whatever you wanted to do. Okay. So device will be opened here in the way it should be opened. Okay. We will have to understand this interface. We will understand this interface like this. This first. Let us have a look at the third view. The two views I have given you now. The first view was this, and the second view was this, and I'll give you another third view that will explain how actually your device will be accessed. So starting with this, the third loop. Suppose there is some application. Okay, yeah, that will execute and give open call and try to open some file. This is, suppose, some file that has to be opened. Now the application will open this file and it will give open system call. See this carefully now. The application will give open system call and will try to open your device by using open system call. Okay. And the control will go to this file which will be called node. Okay. This file will be connected to your device driver, which is your loadable kernel module, through major and minor numbers. You'll have to specify both major and minor number. Okay. This is some LKM. And your file will be the file that you would have created in VFS. This file would be visible in virtual file system and will connect to your device driver using major number to identify the driver and minor number to identify the device. Okay, then there will be some hardware here. That has to be connected. Okay. Now, what happens? The application gives system call and tries to open this file called node. This file is connected to the device driver using major minor number. Before we do anything, you should understand that any device, any file in the file system have a corresponding kernel data structure associated with it called inode. So there will be a struct inode that will be connected with each and every file. Okay, struct inode. I showed you this the other day, that there is something called struct inode, in which there are fields like I_RDEV. There is a field like pointer to file operations, inode. Control will go to struct inode, and inside struct inode it will find some important fields like I_RDEV, device ID. It will have file operations pointer. It will have a pointer to CDEV structure and many more things. This pointer to CDEV will point to structure CDEV, which will be the device specific data structure through which we actually access the hardware device. Okay. The actual access to the hardware device you get through struct CDEV. In struct CDEV also you have some important fields like pointer to file operations, and you have dev, which we checked the last day, yesterday, for major and minor numbers. Okay. Then there is this 32-bit data feed data structure called dev underscore t, which contains major number and minor number, okay, which is accessible from struct inode and from dev as well. We've seen this yesterday. Okay. Now today what happened? The application gives the open system call and tries to connect with the node. Okay. And this node is a file in the file system. It connects to its corresponding data structure, inode. Okay. And inside this inode, hold on. So this is the interfaces that we already have. Now let me put some focus on file operations here, because that is where we are going to work today. There is a kernel data structure called file operations. In which you will have references to routines like open, release is close, write, read, things like this. Okay, and then you will have to implement your own device driver routines. For open, close means release, write, read. Okay, these are the connectors. Now these connectors connect to you to the device driver routines, and this is your device driver routines, which you are going to write from today. Okay. This is the actual source code of the device driver that you have to implement. Now things will happen from here. The very first thing, that the open system call will be given. Okay, the control will come to the node. From there it will go to the inode. Inside inode it will check the device ID. Is it correct? Then the control will go to the struct cdev. Here also the device ID will be cross-verified. If the device ID will be found to be same from both ends, then it will be understood that the interfaces are correct. Then step number 5, the file operations will be used here and here. Step number 5, the file operations will be used. If the struct file operation is found to be a relevant reference to a relevant data structure, then the same interface will be cross-checked from struct dev also, and the same reference is found to be a valid reference, and both will be referring to the same data structure. Then it will be understood that the interfaces are correct. Then step number 6, control will come here. Open system call is given. So step number 7, the open system call reference will be used, and the control will go to the appropriate open device driver routine. The open device driver routine will fetch the device ID and verify it. If the device ID is fetched and verified correctly, then Open will create and initialize a new kernel data structure called struct file. Now this struct file is created and initialized when a stream data channel is created that connects the application and the file to Open in appropriate mode. This struct file will have some important fields like file flags. I'll show you this struct file to you. Yes, Rahul, tell me. हाँ, अलग अलग चीज़ें हैं. हमें वर्चुअल फाइल सिस्टम विजिबल होता है. We always see the virtual file system from application layer. So there is a header file called fs.h in which you'll find struct file. Here is a struct file. Inside struct file you have important, this struct file is, first of all, remember, is a stream representation data structure. It represents the stream, the data channel which is created and connected between the process and the opened file. It tells you the path of the file to open and the inode associated with that node. It also refers to the file operation structure, which specifies what are the file operations applied on the file operation structure that we have created. So another important data structure that we have to use inside this struct file is the file operations pointer. Another or more important things that it contains is the flags, the POS, file position, from where you will do read write. Many things. Private data is another important field that we'll be using. And few more things. So there is a reference to struct file operation here. Now, step number 8. In step number 8, the open routine fetches the device ID and then makes this device ID get stored in private data field. Step number 8A, it fetches the device ID, and step number 8B, it stores the device ID in the private data field inside struct file. This struct file is a data structure in kernel which represents the stream, the logical data channel, which specifies the set of rules for the data transfer from the application through the stream down to the device. This is how the control will reach the open system call routine, and this is how the open system call routine will fetch the device ID and preserve this device ID in the private data field of struct file. After that, the open system call will be over, and even the file descriptor that are stored in fd variable will get destroyed, but the reference to the file will continue to exist here in struct file until unless the string is present. Struct file will be present, and a reference to the already opened device will be stored in private data. Actually, the device is said to be opened only when the device reference is preserved in private data in struct file. Okay. So this is what needs to be done. Normally what happens when the open system call is routine given, the control goes to the system call routine. But in your case, the control will come to device driver routine. Okay. The reason for this is, I will explain you now how the control comes to the driver routine instead of the ordinary system call routine. What happens is, when you create this file, then this file is created using a command called mknode. This mknode takes arguments. First argument is device type. Second argument is file name. Third argument is major number. And the fourth argument is minor number. So it takes these four arguments. So when the file will be created, it will be connected to your device driver using major number, and through the device driver to the actual hardware device, and through the device driver to actual hardware device using minor number. Okay. So this file is, because it will have the major and the minor number, therefore this file will be understood that this file is not an ordinary file that will go and get stored in the device, that will go and get stored in the secondary storage hard drive. Instead, this file is a special device file which will connect to the device driver and further down to the hardware device. Now, if a file is understood to be a device file, then whatever system call comes maps to the driver routine inside the identified device driver. If this file would have been some ordinary file where there was no major and the minor number, then it was an ordinary file. It would have gone to the ordinary system call routine because this was an ordinary file and because this was stored in the secondary storage. Your kernel have open system call routine which can open files from inside kernel, from inside secondary storage, but rest of the world is outside secondary storage. So your kernel does not know how to open your file, your device rather. So therefore the system call routine provided inside the kernel is not capable to open your device. It's you are designing your device. So it's you will design your open routine for your device driver. And then you will create a file using mknode which will be connected to the device driver and the device using major and the minor number. So when the open will go give the system call to open that file, it will be understood as a device file having the major and the minor number. Using the major number, it will go to the corresponding device driver, and inside the device driver, it will find the file operation structure, the open routine, open system call routine, driver routine, which will do the needful and open your device. So I hope you are able to understand what needs to be done. For that, we have to go to the kernel data structure that is provided inside the kernel for file operations. Here it is. Struct file operations. If you look at this, there is an open system call routine. Here you see. This is what we have to use. If you see carefully, it is function pointers. That is the reason that right from the day one, not day one, but from very early stages in C programming when you did, I took you to function pointers so that you don't face difficulty here. So the hard work that you and effort you have put in there will be useful now. The open method. The open method will do what? The four important things that the open method will do, open driver routine should do. Number one, check for device specific errors. There may be possibility that hardware device itself is having some bugs. Initialize the device if opened for the first time. If your device is being opened for the first time, then it will do some initializations which were left pending in the initialization function. And some device parameters had to be set. After that, update the file operations and the file position pointers, both. That file position will specify that you have opened the device, and definitely you're going to do some read-write operations on that, or maybe some control operations on that. Then you have to specify the position from where you will do that inside the file. After that, you fill the file p underscore private data field in struct file. The last step, this you have to fill it. Okay, so these are the four primary things that the open routine have to do. This here is your open routine. Now this open routine had to be understood like this. You have been using this open system call routine ever since the beginning of file IO, where you learn file IO in C programming, isn't it? You know that you give the open system call. You know that the open system call takes the file name as an argument, and you know that you specify the file modes also, like the file will be opened in which mode, open, read mode, write mode, whatever. And you know very well that the open system call returns the file descriptor. Now the open system call that you will give will now map to the corresponding open system call routine. No, open device driver routine. Okay, so corresponding to the open system call given in the application, you will have your own open device routine, device driver routine. The file name that you have given in the open system call, well, the file system doesn't know files, doesn't identify files using file names. The file system actually identifies the files using the corresponding struct inode. You remember I told you that every file in the system have a corresponding struct inode. So the control will go to the corresponding struct inode. So therefore, in the routine, the first argument of open is a pointer to struct inode corresponding to the file name given by the application in the open system call. Second argument was the mode. Okay, the mode is actually referred to by here, struct file, another kernel data structure. Okay, that is struct file which I showed you just now. This, in which there is private data, file position, reference to file operation structure, and flags specifying status of the file. Okay, so we'll have these two arguments in the open system call, and this is the mapping that will happen. Okay, when the open system call and your corresponding open routine will be successful, then a new data channel will be created between the two processes, between the application and the VFS file node. Stream will be created. Okay, and this stream will be the data channel through which you will be able to access, through which you will be able to do I/O. Okay, and a connector file descriptor will be made available in the user space for representing the connections to the file. Right? So, open system call routine. Now there are some kernel data structures like struct inode, struct file, struct cdev, struct file operations. These 4 kernel data structures I have identified to you till now. To know more about these kernel data structures, you don't need to read any document. You will straight away go to struct fs.h header file and see what are the fields in that. Then you will write your device drivers and use almost all the fields present in all the 4 data structures, and that is how you learn. And be patient during the device driver development. Slowly, one by one, you will be introduced to each and every field in that almost. Okay, so now what we have to do is we have to implement this concept through device drivers. Let's go to our device driver. Inside our device driver, we have a file called file operations.h, in which the operations are not mentioned till now. So what we have to do is we have to work on this file operations and keep open and close means release these 2 system calls today. So we'll map here. Open system call, standard open system call will map to my device driver routine. I will call it open dev. Okay, comma. The close means release. System call will be mapped to my driver routine, and I will call it release dev. You notice there is a comma as a separator between these 2. These 2 are actually not data elements that you keep inside structures, which are placeholders for some data. No, this structure is a collection of mappings from system calls to corresponding device driver routines. So 2 system calls, open and released, will be mapped to not the standard system call routines, but to your device driver routines, and you'll call it open dev and release dev. From now onwards, whenever the open system call will be given to your device file, the control will go through file operations, through these red marked steps to struct file operations, and there it will find the open system call mapped to colon to corresponding device driver routine, which we would have written here. Okay, this was struct file operations. Now let's go to declarations.h and declare, as you promised in struct file operations, that you are going to have a device driver routine with the name of OpenDev. The prototype for this OpenDev is given here. It will return an integer. It will take a pointer to struct inode and pointer to struct file as argument. Just now I explained you why you have these arguments. So it will return integer, and the arguments will be struct inode pointer and struct file pointer. Okay, we have implemented struct file operations. In struct file operations, we have implemented mapping for release dev also. So in struct file operations, just after open here, you have prototype standardized for a release system call that also takes pointer to struct inode and pointer to struct file as argument. So let us give the prototype for release dev also. The prototype is same. Now we have to implement these two device driver routines, which will actually do the opening stuff. OpenDev.c. So we'll implement this OpenDev.c here. Return type integer, name is OpenDev, and the arguments are struct inode pointer, give it a name inode p, and struct file pointer, let's call it file p. That's all, a simple routine in which we don't do anything as of now. We just leave it empty with the begin and that's all. Nothing much. We have to have another device driver routine for close, release. So this is release dev. There it is. So there it is. We have the OpenDev and the release dev, both functions, both driver routines rather, implemented and mapped through file operations. And to build it with device drivers, you have to update the corresponding. You have to update your make file also, and you have to say that other than init.o and clean.o, you also have opendev.o and release dev.o also, which will ultimately create your CDD 150 and complete object module for CDD 150.o. Fine. Let's test it using test script. One for check-in, declarations.h, declared driver routines, for OpenDev and release dev. What else? In file operations, mapped standard system calls for open and release. Init.c, we don't do anything. In OpenDev, this is the driver routine for opening device, just checking mapping for now. This is the driver routine for closing or releasing device. Just checking mapping for now. That's it. So check-in is done. Now check out for build number 2. Number 3 build. The driver build is happening, and open and the release dev will also open dev.o and release dev.o will also get compiled. There is some bug in init.o. Okay, fine. So we'll do checkout for development number 6 and 0 for exit. So in it we introduced some bug actually by mistake. Memset, we did memset. Test script once again. 1 check-in, there is some typo. 2 checkout for build. 3 build. Driver build happened successfully. Notice open dev.o and release dev.o were also compiled. Then number 3 build the driver is done. Number 4 insert your device driver. So this is ls mode. The device driver is inserted, and here you see right at the top cd150 cat/proc/devices shows you that your device driver is inside the device table here. This is cat/proc/modules that shows the list stack of modules. Right at the top of the stack you have your own module, and there you see major number 238 and number of devices 20, and all the 20 minor numbers are here. Okay, then we have to do remove device driver number 5. Remove ls mode shows you that the device driver is removed and your device will not be visible. It is not visible. Then cat/proc/devices shows you the device table, and 238 your device driver is gone. Cat/proc/module shows you the list of stack of modules, and you see at the top of the stack your device driver is gone. This is important to test everything because you see notice Vansh asked in the beginning of the session that his driver is having problems. So you will come to know about those problems only from these entries. Okay, cleanup is over, and then check out for development number 6 and exit. Yes, gone. But we could not test our open and release routines. The reason is this: we do not have any applications as of now which is opening our device, which is giving the open call. Only when the open call will be given, then only through these steps open routine will run. So we need to write these multi-threaded applications, which will be the topic of our next class, where we will write the applications, multi-threaded applications, to test our device driver. Okay, chalo, that's all I have for you now.